o'clock, so we are going to go ahead and get started. If you have not been to a First Saturday seminar before, welcome. We're glad to have you. My name is Marissa Blackburn. I am our Environmental Education Manager here at Cape Fear River Watch. And just ignore this mic that I'm holding. It's just for our audio recording that we're going to be doing. We'll be posting a video of this seminar on our website next week and on our YouTube channel as well. So if you want to share, you can access it that way. I'm going to go ahead and share a couple reminders and upcoming events for Cape Fear River Watch, and then I'll turn it on over to our speaker for today. So today, after our seminar, starting at noon, we have we're partnering with the Arboretum to do a medication disposal take-back event that our public health intern, Katie, for the spring in the back there, has helped to organize and coordinate for us. So we really appreciate her hard work on that event. If you have any used, expired, unwanted medications in your home lying around, liquid medications or pills, you can bring those to the Arboretum from noon to 2 o'clock today, and we will take all of that stuff back. If it doesn't work out, if today's not a good time for you later, there are a lot of drop boxes throughout town that are just open 24/7, and you can use some of those as well. If you want more details, you can talk to Katie after our seminar today. Next week, we have our second Saturday cleanup at 9 o'clock. Rob coordinates those, and I don't know where we're doing it next week. So if you want to participate, get in touch with us over the next week, and I'll let you know, or Rob will let you know. We'll also be posting about it on our social media accounts. The following Saturday, we have our paddle. This month, we will be paddling the Black River and launching from Ivanhoe, which is up a little bit ways out of town. It's going to be on the Black River up before the Three Sisters Swamp. So we won't be doing Three Sisters Swamp paddle, but it will be a beautiful stretch of the Black River that our river keeper Kemp will be leading. So if you want more details on that, you can let me know after our seminar today. And then we also have our April Eco Tour on April 18th, which is a Tuesday morning at 10 o'clock. It's an hour eco tour around Greenfield Lake. We had one in March and we had one in February, but if you haven't been able to get out to one of those, we would love to have you. All right, well with that, I'm going to introduce our speaker for today, Dr. Frederick Bingham. He is a professor in the Department of Physics and Physical Oceanography and the Center for Marine Science at UNCW, and he's been there for almost 30 years. He has a PhD in oceanography from the University of California, San Diego, and a master's degree in computer science and information systems from UNCW. He's held previous positions at Tohoku University in Japan and the University of Hawaii at Manoa. He spent his career studying the circulation of the oceans at large scales, their interaction with the atmosphere, their role in the climate, and the importance of ocean salinity and all of that. He has over 50 published papers in the field, and his research has been funded by NASA as a member of their Ocean Salinity Science team since 2009. So I'm excited to turn it over to Dr. Bingham.
Thank you. Thanks, Marissa.
I'm going to pass around our sign-in sheet.
All right. So I want to talk to you today about salinity and sea level rise and how the ocean is observed. Yeah, so this quote up here is one of my favorite ones. It says, "All the rivers run into the sea, yet the sea is not full. Unto the place from whence the rivers come, thither they return again." Isn't that a beautiful quote? So the people who wrote this really understood that rivers are part of a cycle. The ocean is not like a bathtub where water goes into it and it fills up. There's a cycle of water that goes on, and they had some understanding of that, which is really cool. Just a little about me beyond what Marissa has just said. I'm an observational physical oceanographer. So what that means is that I study the physics of the oceans, the physical aspects of it, temperature, salinity, the ocean currents, interactions with the atmosphere, tides, anything that you would associate with physics and the oceans is what I study, or is what I specialize in. So if you're going to ask me a question about fish or dolphins or whales, I will have a lot of trouble giving you an answer. So as Marissa said, I study ocean salinity at the basin and global scale. So I really look at large scale stuff, things that go on at hundreds or thousands, tens of thousands of kilometers in scale. And as she said, I've been funded by NASA to do my research since 2009. Yeah, so a lot of times I feel like Peppermint Patty in this cartoon, where she says, you know, she's kind of bogged down about, she says, the ocean, a report. The ocean is full of water. Ha, you may say, what else? That's a good question. She ponders. Sometimes it's easy to get bogged down on these reports. So I feel like her a lot of the time. But so the ocean has been observed systematically for a very long time. The first oceanographer was actually none other than Ben Franklin, who was the Postmaster General of the United States, or the colonies back then. He actually drew this map of the Gulf Stream, which is actually a fairly accurate map. It's a really nice map of the Gulf Stream. He drew this using ship logs and observations from captains and so forth, and also measurements of temperature, surface temperature. So he was the first person to measure the Gulf Stream systematically. More recently, this is the kind of stuff that I do. So these are the kinds of observations that we're making now. There's a huge infrastructure of ocean observations that people in a group like this probably are just unaware of. And this is one of the main ones. This is one of our main tools for observing the oceans. They're called Argo floats. There's an Argo float actually in person sitting up there on the deck of a ship up on the top left. It's about 5 feet tall. The way they work is they spend most of their life at about 1,000 meters depth, which is about 3/4 of a mile deep in the ocean. They have a 10-day cycle. For 9 of those days, they just float around wherever they go. And then at the end of 9 days, they will descend down to 2,000 meters and then profile all the way up to the surface, send their information up to a satellite, and then go back down to 1,000 meters. That's and up on the top right is just a typical temperature in black and salinity in red, typical profile, the type of data that these things collect. At any one time nowadays, there's approximately 4,000 of these things. So there's each one of those little dots is a location of a float that surfaced within the last 10 days. So we get a lot of our information about the ocean from stuff like this. There's also this giant array of moorings out there, mostly in the tropics, not all, but mostly. Each of those dots on this map at the top left is what's called a part of the global tropical moored buoy array. So there's 130 or so of these moorings stretched all the way across the tropical oceans, started in the tropical Pacific and expanded into the Atlantic and the Indian. You can imagine this is an enormous operation, trying to keep and maintain this number of buoys. Why are they there? Well, they're mostly there to measure and understand El Nino. They were first proposed and put in following the 1982-83 El Nino event, which really took everybody by surprise. So after that event, and it caused a lot of damage too, after that event there was a feeling that we really had to begin observing El Nino because it had such a huge impact. And so they put in the Pacific array first in the 90s, and then the Atlantic and Indian Ocean parts followed. At the bottom is a typical type of data reading that you would see from them. I'm not going to go into the details of it, but the array is really used to understand the status of El Nino. So you can go at any time and look on the NOAA website and find the forecast. So they make forecasts of El Nino conditions going forward for a few months nowadays. And this is the primary source of information where they get all that information from. That's how they know. Another thing that's measured commonly is sea surface height or sea level. We all understand what that means, the ups and downs of the tides. There's a sea level gauge practically a stone's throw right across the river, right underneath the bridge on the other side. There's a picture of it. That's the Cape Fear Memorial Bridge down on the right-hand side. And in the top middle there is a record. These observations have been going since the 1930s, so almost 100 years now of observations from the tide gauge right across the river. Isn't that cool? And you can see, obviously, that the level is going up. It may be hard to see with the left-hand side. You can't really see the detail of it, but since it started to present day, sea level has gone up by something like a foot, 30 centimeters or so. You'd also notice, if you look at this carefully, that the last 10 or 15 years, right over here, that rate is actually accelerating. You can see it. The slope is a lot larger. And this part down here is just to indicate that these gauges have to be very carefully calibrated and leveled to make sure that they're always measuring the height of the surface of the ocean and not changes in the land. There's actually an enormous network of these things all over the globe, everywhere around the ocean. Each one of the dots on that map is a tide gauge that's followed. And you can't really see this, but various people have used these tide gauges to measure rates of sea level rise. And let me go back to the previous one for just a second. So there's our Wilmington one. You can't really see this on your it's not well enough focused. But if you look up here, right there, that number, it says 2.61 millimeters per year. So that's, if you look at that line and you figure out what the slope of the line is and how fast it's rising, that's what you get. So the number that I want to, okay. Oh, great, thank you. Sorry, there you go. Oh, perfect, thank you. This number here is, so the number that I want you to keep in your head is about 3 millimeters per year. 3 millimeters per year. This says 2.61, but we'll just round it up, because obviously it's rising a little faster. 3. Anyway, people have used other tide gauges, this whole network of tide gauges, to make estimates of how fast sea level is rising. And there's various estimates from various different people using different methods and over different time periods. But anyway, this tide gauge network is an important aspect of the way we observe the oceans. Now I want to talk a little bit about satellite observations. Satellites are commonly used to measure the oceans. It's an important part of the work that I do. Satellites routinely measure sea surface temperature, sea surface height or sea level, gravity or mass, which I'll talk about, sea surface salinity, which is really my specialty here, ocean color or productivity, the biological activity within the oceans, and surface winds. They can measure how fast the wind is blowing on the surface of the ocean, which direction it's going. This here is that's the Aquarius satellite, which I'll talk about in a little while. So why would we measure sea surface temperature? What's the purpose of measuring the temperature of the surface of the ocean? Well, there's an obvious connection between ocean temperature and the climate. This figure down here really says a lot. According to the IPCC, the Intergovernmental Panel on Climate Change, of all the excess heat that we're putting into the Earth, of all that excess heat that the Earth is absorbing, 90% of it has been absorbed by the oceans. So when we talk about climate change, we have to talk about the ocean. That's where it's all going on. I like to think of the dog analogy. The dog is the ocean or the climate, and the tail is going along behind it. You know that with the dog, the tail's going to wag around and do whatever it wants, but ultimately it's going to follow along with the dog. It's not going to go anyplace different. So another really important idea here is that the top 1 meter of the ocean, the top 3 feet of the ocean, has the same heat content as the entire atmosphere. So in other words, the amount of energy that it takes to change 1 meter of ocean is the same as the amount of energy to change the entire atmosphere. And as you'll see, ocean warming is going several hundred meters deep into the ocean. So this is a picture of sea surface temperature. This is the kind of thing that you see on a day-to-day basis. There's a lot of really cool detail in this picture, which I'd love to spend time talking to you about, but there's just not enough time to go into it in a lot of detail. But this here is a sea surface temperature anomaly, which is like how different the temperature is from normal, right? Is it hotter than normal? Is it colder than normal? And you can see all these red patches here. This is just a picture from a couple of weeks ago, just a random day, and you can see all these red patches. What do the red patches mean? They just mean that the ocean is hotter than the average, and that's just typical. You get on any day and you see this kind of thing. These numbers get to be something like 2 to 3 degrees Celsius, 4 to 6 degrees Fahrenheit. So there's all these marine heat waves that are going on. That's what they call them, marine heat waves. So with our satellites, we're able to measure this kind of thing. With the current state of the sea surface temperature, so this is the sea surface temperature in 2021 relative to this long-term average. 2021 was a bit of an unusual year because there was a La Nina event. So you can see that the Eastern Pacific was actually relatively cool. But much of the rest of the ocean was hotter than normal in 2021. And I imagine when the 2022 analysis comes out, this entire thing will be red and yellow. This picture here is just somebody's doing an average of the sea surface temperature over time, and you can see how starting in 1950 here, going up to the present, sea surface temperature is just rising and rising and rising. Total amount of change is something like 3/4 of a degree Celsius. Now, subsurface temperature is largely measured by these Argo floats that I showed you before. The top panel shows what's called the ocean heat content, but what you should think of it is the average temperature. Like, what's the average temperature over the top 700 meters of the ocean? And you can see that it's relentlessly rising, relentlessly going up. So I challenge you to look at this and tell me that global warming is a hoax. I mean, I challenge you to try to do that. And another thing that you can see is that the Argo, we started putting out Argo floats right around here. And you can see, so the different curves are different estimates that people have made using different methodologies. So you can get a sense down here of how noisy it is, how uncertain it is. But once you put all those Argo floats in, we really know very well how fast the ocean is warming. So this is the upper 700 meters, the upper, half a mile or so of the ocean. This is 700 to 2,000 meters, so this is all the way down to close to 2 miles deep. We really don't know anything about what's going on deeper than that, the deep ocean down to, all the way down to the bottom. we don't know about we don't really know much about that. Argo floats don't go down there. But there is some warming going on in this deeper level as well. Satellites can measure, essentially weigh the ocean. They can weigh the Earth. It's really an amazing technology. This mission called GRACE, Gravity Recovery and Climate Experiment, it's just two simple bodies, orbiting bodies. They follow one behind the other, and they measure very precisely the difference between the two. It's kind of like, imagine two cars going down a roller coaster. You have one going down, and when one hits a hill, it will start to go slower, and they'll approach each other. And when they go over the hill, they'll pull apart again. And that's related to the amount of gravity, the amount of stuff, the amount of mass that's right underneath. And so these satellites can essentially weigh the Earth. It's really cool. And very simple. The measurement is very, very simple. The mass of the ocean, so what that means is just the total amount of water, the weight of the water in the ocean, is increasing at a rate of about 2 millimeters per year. Remember, the total sea level rise is about 3 millimeters per year. That's largely due to ice loss in Greenland. So here's a graph of Greenland, the ice in Greenland, the mass of ice in Greenland, and how it's decreasing over time, very, very rapidly. Greenland is melting. There, it's going down, and that's largely causing this 2 millimeter a year rise in sea level. And by the way, if you're interested, there's a really nice New York Times article on the GRACE mission, actually focused more on terrestrial applications. This satellite can actually measure droughts. So if there's a drought going on and there's, there's water, a deficit of water, the satellite can measure that. Isn't that amazing? So sea surface height, satellites can measure the height of the sea surface. The way that the measurement works is very much like one of these digital laser rulers that you would get at Home Depot. Have you seen one of those? You just point it at the wall and you can read how far away that wall is. So what's going on is it measures the amount of time that it takes for the laser light to get to the wall and come back. And that's very much what's going on with the satellite. So the satellite just sends down a pulse of radar and measures the amount of time that it takes to get back. The accuracy is really, truly amazing. So it's less than a couple of centimeters. The accuracy of current altimeters is something like 1 to 2 centimeters. So the satellite flies over, shoots its radar beam down, and measures the distance from the satellite to the surface of the ocean with an accuracy of 1 to 2 centimeters. It's like being in Washington, D.C. and having one of these gizmos with you and pointing it at some buildings in New York City and watching them sway back and forth in the wind. It's really amazing. There's a number of these altimeter missions that have gone on. The most important one was this one called Topex Poseidon, or the initial one, the one where it got really accurate. The current series is called Jason. So there's Jason satellites that are up there. Anyway, if there's one image that I'd like you to take away from this talk today, it's this one here on the top left. So let me explain what's going on here. This black curve is the global average sea surface height from the satellites. And you can see that it's relentlessly going up, going up, going up. And they're measured using these altimeters, these satellite altimeters. And the rate is actually 3.4 millimeters per year. So why is sea level rising? I already said that one reason sea level is rising is just there's more water in the ocean. Right? And that's ocean mass, and that's measured by the GRACE satellite, and that's what the blue curve is. And that turns out to be about 2 millimeters per year. What's the other reason sea level is rising it's because the ocean is getting warmer. Just like anything that gets warmer, it will expand, right? So think about an expansion joint on a bridge. Why do bridges have expansion joints? Because the concrete gets warm and it expands, and you don't want that to cause the concrete to buckle. And so the ocean is getting warmer, and as it gets warmer, it expands, and the rate of expansion is something like 1.2 millimeters per year. So that's the red curve. This purple curve here, I don't know if you can see it right there, it almost directly follows the black curve. The purple curve is the sum of the blue and the red. So here are 3 measurements of sea level rise that are taken completely independently. The temperature measurements are done with these Argo floats. The mass is done with GRACE. This is done with the altimeter. And so it's 3 completely independent ways of measuring the rate of sea level rise. And they agree with each other almost perfectly. So it's really pretty well documented what's going on. We really have a pretty good understanding of how this is all going. This graph down here it's a picture of the sea level in 2021 versus some kind of an average, a previous average. And you can see it's all red, which means it's all higher. It's not completely uniform. Some areas are rising faster than others. So the Eastern Pacific maybe not as fast. Anyway, and this is Jason 1. That's one of the altimeter satellites. So this is just the same graph that I just showed you, this black curve. I'm just going to show you another version of it. And what I want you to see here is this blue line here. That's like a mathematical fit to these data. And what you should notice is that this line is not straight. It's not straight, right? It's curving upwards. And so here's that 3.4 millimeters per year, which you may not be able to see there. Down here is what's called the acceleration. So it's 0.08 millimeters per year per year. So in other words, if it's 3.4 millimeters this year, it's going to be 3.48 millimeters next year, 3.56 millimeters per year the year after that. You see where I'm going with this? Yeah. So the rate of sea level is not only going up, the rate of sea level rise is increasing. So there we go. I think that sea level rise is going to be one of the prime, things in our lives over the next few decades. All right. So that's sea level rise. I want to spend a few minutes talking about salinity. I could actually give a college course in salinity, just like a whole course. But I don't want to burden you with that. But salinity is something that I've been studying for most of 30 years, as Marissa said, so I know a fair amount about it. First of all, how do we define the salinity of water? It's the number of grams of salt per kilogram of seawater. So imagine taking like a soda bottle full of seawater and evaporating away all the water. And what you're left with is a salty residue at the bottom, and then you weigh that. That would be the salinity. It's measured using conductivity, which is the ability of water to conduct electricity. So you stick electrodes down there and measure how well the water conducts electricity. This is a typical cell which measures a conductivity cell. Modern units is PSS or PSU if you ever see this. Typical ocean values are somewhere between 33 and 37. That's the kind of value that you would see in the ocean. It's a little more difficult to measure than temperature. It requires calibration and is very sensitive to fouling and stuff. So it's not completely trivial to measure, but it's relatively straightforward if you're careful. So why do we measure salinity? What's the importance or interest or use in measuring salinity? Well, it's very closely tied to the global water cycle, as I'll show you. This is not very, the quality doesn't come through here very well, but this is a map of average sea surface salinity over the Earth. And you can see that that's North and South America, Africa, Europe. And there's, you can see that there's some areas that are very salty, especially like in mid-latitudes. Here in the North Atlantic is a very salty ocean. And this very salty area somewhere between the Sahara and the Caribbean is very, very salty. Over here on the right is the average rainfall over the ocean. Again, it's a little hard to see, but these very salty areas in mid-ocean are actually very closely aligned with these areas where rainfall is very low. And so salinity gives you an indication of how much it's raining, how the water cycle, how water is getting into the atmosphere and being rained out onto the ocean and so forth. So it's an indicator of the water cycle. The water cycle, of course, is a very important part of our lives. You know, we have to have water, fresh water, in order to live. Ocean salinity, I've showed you how ocean temperature is changing. Ocean salinity is changing as well, and in a way that's not consistent with natural variability. An important fact here is that 86% of evaporation and 78% of precipitation occur over the ocean. The difference between 86 and 78, well, that's really crucial for us, because that's the water that ends up on land that we can use for drinking water, for rivers, and so forth. Yeah, and changes in surface salinity may be a useful indicator of future precipitation on land. This is actually my current research direction. This is what I'm researching very vigorously right now. One of the highlights of my career was back in June 2011. I attended the launch of this satellite called Aquarius. That's the Aquarius satellite right there. Aquarius is a satellite which measures salinity, ocean salinity from space, from a satellite. There's actually 3 of these. Aquarius actually died in 2015, but there's another similar one called SMAP, which is up there right now measuring salinity. And so I was in on the ground floor. I spent a lot of time preparing for this mission, and was one of among the first people who were able to look at the data that came out of it and so forth. It was a very exciting thing to be involved in. So measuring ocean salinity from space, people ask how this works, and I don't want to get too much into the weeds here. That's not really, I put an equation down here, but I want you to just ignore that. Just realize that there's a lot of pretty complicated mathematics going on here. What I want you to mainly look at is these 2 pictures over here. One is just a regular zebra, and one is a thermal infrared picture of a zebra. And you'll notice, if you take a thermal infrared picture of a zebra, you'll notice that the black stripes look hotter than the white stripes. Why is that? Well, it turns out that black is more efficient at radiating energy. It looks hotter to the camera. So it's the efficiency at which energy is radiated from this body that is the quantity that we actually measure using the satellite. That quantity is related to the conductivity, or the ability of water to conduct electricity. So in a very short nutshell, that's how this technology works. There's way more complications to it than that. I've sat through hours and hours of presentations on it, but that's the basic idea. Amazingly enough, it all works. It's really a miracle. So salinity, as I said, is changing, and I don't want to bog you down with too much of this kind of stuff. Salinity contrasts are increasing. That's basically what's going on. So we all know about all these floods and droughts that are going on land. We read about them in the paper every day, or in the news every day, about all these floods, droughts, crazy weather. All that stuff is going on in the ocean too, obviously. And so how do we know that? Well, we look at the salinity as one way of being able to tell what's going on. So salinity contrasts in the ocean are increasing. Fresh areas are getting fresher, salty areas are getting saltier. The main thing to look at here is maybe the North Atlantic, which is a relatively, as I said, a relatively salty area. This color is the change relative in 2021 relative to 2000. And so you can see that the North Atlantic is not only salty, it's also getting saltier. And so these contrasts are increasing over time. And it's basically like the impact of droughts and floods in the ocean. As I said, a lot of climate change is going on in the ocean as well. And the aspects of the global water cycle are there. All right, so since this is a group that is concerned with the Cape Fear River, I thought I would spend a little time talking about salinity in the Cape Fear River, which is totally not my specialty at all. But I want to talk a little bit about that because I thought that would be of interest to this group. I looked into how salinity is monitored in the Cape Fear River and didn't come up with much. That's why there's nothing on this slide. So I should caveat that that's not completely true. There's this program called the Lower Cape Fear River Program. Which, is anybody here affiliated with that? No. So they go out and they actually sample salinity weekly in the estuary, so south of downtown, and twice monthly in the river in the summer and monthly in the wintertime. So there is some sampling going on. It's hard to see. I'm sorry about the quality of this, but I asked them to send me the data that they'd collected. And there it is. It's a hash. There's not really much you can get out of it. You know, try and determine a trend from that, right? And so the sampling that they're doing is not really adequate to determine really changes in salinity over time, which is what we really want to know. Like, we really want to know, is the river getting saltier or not? That would be really important information for us to know. And just a little bit about, this is more of an idealized picture of what salinity in a river like the Cape Fear River would look like in an estuary. So here you have the ocean, and here you have the river coming down. And you have what's called a salt wedge, right? The salt wedge, with the salt wedge you have salty water that comes in because it's so much denser. It comes in at the bottom, and then you have fresh water coming in at the top. And these two overlay each other. This salt wedge, and there may be people in this room who actually know how this works a lot better than I do, but the salt wedge, this salt wedge may go the entire length of the river. It may go from Southport all the way up to downtown, or it may be just a mile or two, or it may actually be vertical. Instead of a wedge like that, it may just be like that. Or this is showing a very sharp contrast between the surface, between this fresh water and the salt water. It may be a lot less contrasty. It may be a much less of a gradient. And so the structure of this will vary depending on the tidal cycle, depending on how much discharge, like how much water is actually coming out of the river, how much what the winds are. It all varies, and so it's quite a variable system. There's a lot going on, and so if you think about this and you go back to the idea that this is being sampled monthly or twice monthly maybe, you can see that that's probably not an adequate way of sampling to try to determine whether salinity is actually increasing, whether it's changing in the river. And so, unfortunately, it's actually trees like this that are doing, dead trees like this in the estuary that are doing a much better job of monitoring the salinity in the river than we humans are. We think the river's getting saltier, we think it will get saltier as they do this dredging they're talking about, but there's no baseline, there's no plan to monitor any of it. Whatever happens will just happen. So it's kind of sad to think about, but yeah, that's where we seem to be. So with that, I'm going to close. That's my contact information if you're interested in talking about this some more. If you're interested in climate in the future, this website, ipcc.ch, the Intergovernmental Panel on Climate Change, there's all kinds of really interesting information there. This synthesis report is really good. So with that, I'm just going to open it up for questions. Yes?
Does the satellite data exist to infer salinity in the river from satellite data?
That's a great question. So let me go back to that's a great question, and there's a lot of technical stuff that goes into the answer. But what I'll tell you is there's a resolution. Oops. So think of the satellite as a 1-pixel camera, right? So it's just going along and taking one pixel. But that pixel on the surface of the Earth is something like 70 kilometers wide. So obviously it's not going to be able to do much for getting into the river. You see, this is the more recent satellite. This antenna is 6 meters wide. The wider the antenna, the better resolution you can get. But getting an antenna like that into space is a real technical challenge. And so 6 meters is probably as good as they can get. It's just physics. It has to do with the frequency of the radiation they're using. So, yeah.
The answer is no.
The answer is no. Sorry. I could spend, remember the college course thing? I could spend an hour talking about how that works, but I'm not going to bore you with that. Yeah, all the way in the back. Yeah.
The flow rate difference between river, estuary, and ocean, I'm guessing would cause laminar and disruptive flow between those?
Yeah.
Is that a type of mixture that we can track, or is it going to help us?
It's certainly possible to track it. I mean, they could, if we wanted to, we could produce a model which actually, simulates this.
I'm
it would.
guessing there are different rates.
Yeah. They're flowing over each other at different rates. Yeah. And they can model the processes that go on as the mixing processes that go on between the fresh and the salty water. And there's people that are doing that. I actually have a colleague that's working very hard. A graduate student, their graduate student is working very hard on a model that models the Albemarle Pamlico Sound. We could make one of those for the river if we wanted to. Yeah.
It annoys me that the sea level rise isn't equal.
Mm-hmm.
So I know there are currents and winds, but you can kind of rate the top 3 or 4 forces or mechanisms. And sub-question is, does the Greenfield ice sheet actually have its own gravity?
Yeah, the Greenland ice sheet exerts its own gravity. Yeah, it's a giant, massive thing. So obviously, it has its own gravitational pull. And as the water melts out, it decreases over time. So obviously the different parts of the ocean are rising at different rates. Why that's going on, why some areas are rising faster than others. People are, that's a research topic. People are trying to figure that out. So I'm guessing this particular picture had a lot to do with that La Nina event I was talking about because of the cold water. Maybe that decreased the sea level rise in the eastern Pacific. Yeah. I'm not sure if that answered your question or, yeah.
It's not well known or something.
Yeah. People are trying to figure that kind of stuff out. Yeah. Yes.
Given what you've talked about
Mhm.
as far as salinity,
Yeah.
ocean level rise, and and temperature rise,
Yeah.
how does that, is there any correlation with that regarding the dredging of the Cape Fear?
Yeah. I think everybody expects that as the Cape Fear is dredged, it will get saltier, and it will start rising faster. So, remember I showed you this picture, this one that I didn't know what it was doing there. I think, and maybe there's people in this room who know this. There was an earlier round of dredging, and I think it occurred right around here, right? Anybody know this? When that occurred? Yeah, they went from 40 feet to 43 or something. I can't remember.
Late 90s or early 2000s?
Yeah, that's right here. Yeah. So when they did that earlier round of dredging, that really started this accelerated sea level rise. And I imagine when they do this new round of dredging, did anybody go to that forum over at UNCW? Yeah.
Can you speak to whether anybody from the Port Authority that's proposing this dredging talks to people like you?
I can assure you very, very, very vigorously that they do not talk to me. So I went to that forum and I asked the guy from the ports, I said, well, what sort of environmental monitoring are you planning, to monitor the impact of this dredging? And the answer I got, I don't remember what the answer was, but to me, my recollection is it was a word salad that basically said, we're going to do this report and we're going to get our permit and then we're done. We don't actually, la, 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 la. We don't really want to know what's going on. So, yeah. And if you think about this, right? So if we want to monitor salinity in an estuary like that, sampling once a month is just not going to do it. It's just not. What you need is, so this trend here is measured over decades and decades, and it's an instrument that's out there measuring continuously. It's measuring, like they put out a measurement once every hour from that instrument out there. And so I think if you really wanted to monitor how salinity is changing in the estuary, you'd have to do something similar to that. You'd have to put out an instrument. You'd have to put out instrumentation that measured almost continuously. You'd have to have somebody that really took care of that instrumentation and kept it calibrated, looked at the data, and made sure it was measuring correctly. Yeah.
Does that instrumentation exist?
Yeah, sure. That kind of instrumentation is perfectly available. It's not cheap, but it's certainly possible
We
too.
just need somebody to take ownership of the placement and monitoring and maintenance.
Exactly. Yeah. I wanted to show you this. I put this as an extra slide. This one. I'm not sure if you can see this, but if you go to Tampa Bay. Tampa Bay has this thing called a port system where they have all these monitoring stations stationed all over the port, all over Tampa Bay, to measure stuff like tides, temperatures, salinity, all this kind of stuff. And this is really crucial for their cruise ship industry, the port traffic that they have coming in and out. It's really crucial for that stuff. And I actually have had some minor amount of discussion with the local port about putting in a system like this. This is something that I think would be really, in fact, I'm amazed they don't already have something like this in the river here related to the port. I can't believe that the port would not absolutely need to know what the salinity is, because how salty the water is tells you how high the ships are going to float, right? So I can't believe that this doesn't already exist in the port here. But you know, I'm just an ivory tower guy sitting in my lab doing my research. So I don't make those kinds of decisions.
Dig a deeper hole.
Yeah. Yeah. So I think, I mean, we've had some discussions about putting in this kind of a system. It's a matter of funding and getting the right people involved. The port's occasionally gotten interested, but never really followed through. So, yeah, all the way in the back.
I'm wondering, like, about how much it costs. And if you have, like, an idea of, like, other organizations that might, like, be willing to, or, like, that would be a good organization to kind of take charge of monitoring these kind of things. Like, if you even have, like, multiple monitoring stations, that seems like would be ideal.
Yeah.
Multiple, and then I think the port seems like they wouldn't really want to monitor because then, like with the dredging, they know that it's going to increase the salinity a great amount. And
Exactly. Yeah, precisely. Yeah, right. Yeah. I can't speak to their mentality, but I do know. And in case you don't know, there's a proposal out there to take the current river channel and deepen it to 49 feet. Anybody more familiar with this than I am? Yeah, I think they want to take it from 43 down to 49 feet. So it's a lot of digging. It's a lot of digging and a lot of dredging and a lot of impact.
Yeah. And there's an environmental impact study going on.
There's an environmental impact study going on. That's what the guy was talking about, the study that
That's
they're
being
doing.
conducted by the
The Corps of Engineers, yeah. So they're studying that matter right now, what the results of that. I'd love to see a copy of that study when and if it comes out. But this would be the organization. I'm sure they'd be happy to, in answer to your question, I'm sure they'd be happy to take extra money and put in extra instrumentation. So, but it's a matter of funding. Like, who's going to pay for this? And I don't know. Yeah.
How does dredging increase salinity? What's the physical process there?
So, if you look at this, this freshwater plume it's a good question. This freshwater plume, this is just, I don't know this, it's just a guess. This freshwater plume is really not going to change very much because, the river is the river. But when you take the bottom and you actually dredge it down to here, you're putting more salt water farther up into the estuary. And the salinity of the estuary is going to be a matter of like how much salt water is mixing into the river water. And so the farther the saltwater wedge gets up into the estuary, the more mixing is going to go on, and the saltier it's all going to get. Yeah, it's just taking the same amount of fresh water and adding more salt water. It seems logical that it's going to get saltier.
And the trees agree.
And the trees very much agree with that. Yeah. Yeah. They're doing a good job of monitoring all this for us. Yeah.
Question. You said in 1982, 83, there
Mhm.
was, and forgive me, I forget
An El
what it
Nino
was.
event. Yeah.
La Nina?
That was 2021 La Nina. Yeah.
No, but in 1982, 83, there was a significant enough event.
An El Nino event.
El Nino.
Yeah.
What
They're kind
was
of
that
opposite.
I
80,
mean, but you said it was El Nino.
El Nino, yeah, they're sort of opposite. I could give a college lecture on this one, but the 82-83 event, typically when you get an El Nino, there's like a lot of rainfall in flooding and rainfall in California, the West Coast. You get fish die-offs off of South America and so forth.
Right.
And they vary in severity. Some are very severe, some are relatively mild. The one in 82-83 was a very severe one.
Okay.
Does that answer your question?
It does. So there wasn't an event comparable to that prior to 82, 83?
Oh, there were plenty of them. Yeah, there were plenty of them.
I
Yeah.
just wonder why 84 was the time that not you, but the
Yeah.
satellite was put up, or whatever.
The mooring
model
array was
Yeah.
starting to be put in at that point. Yeah, I guess it just started dawning on people that, well, maybe we could, maybe we have the technology where we could actually measure this. Models were beginning to be better at these things, computer models, and so I guess people sort of got together and decided that this was something that could really be helpful, and it has been. It's been immensely helpful to have this information, to be able to make these forecasts. Yeah. All the way in the back?
I was curious, you're talking about the fish kills. So does the salinity, like the increasing level, does it have like a pretty drastic effect on the wildlife? Marine wildlife? Or
Yeah.
Is it anything, or is it kind of like, it doesn't affect them too much?
That is a great question, but you have to remember, let me go back to my first slide. Yeah, I'm a physical oceanographer, so I can't really speak much to that. I haven't taken a biology class in a while, and I don't know like how much salinity it takes to kill a cypress tree. I have no idea. I don't know. It would be interesting to know that, but yeah.
All of the tons of plastic trash that are floating around in the ocean,
Yeah.
does that affect any of the satellite readings, or is it granular?
So I've been out in some of these locations where some of this stuff happens. I think it's a little different from what people think about. It's not like there's like floating mats of trash. There might be like one piece of trash per square meter or something like that. So it's not really something that impacts. It impacts ocean life quite a bit, but I'm not. It's not something we could see in a satellite. Yeah, yeah.
Do you have any idea under the various IPC scenarios of temperature increase in the atmosphere, how much the ocean's going to increase with that?
Yeah, the ocean is whatever temperature the ocean gets up to, that's what the atmosphere is eventually going to get to as well. So this 1.5 degree C threshold they're talking about, that's where the ocean's eventually going to get to. Yeah, as I said with this analogy here, yeah, wherever the ocean goes, that's where the atmosphere and the land are going to go.
I guess, do you have any guess on what the final ocean horizon is going to be?
No, it all depends on what we do as a species about our fossil fuel consumption.
If we were to cut fossil fuels by 2050?
I couldn't answer to any of that. Some of that kind of stuff is in the IPCC report. I couldn't answer it off the top of my head. It's something that could be seen in that report. Yeah.
You pointed out that the line
Yeah.
is curving. In other words, and what I was wondering was, to what extent is that curvature kind of baked in? In other words, is it going to happen no matter what?
I think a lot of it is. Yeah. I think a lot of it is
Like-
baked in. Yep. Yep.
So this may be this idea of doing something about climate change may be like a wishful thinking?
I'm not that cynical. There's lots of different scenarios. If you go to that IPCC report, there's lots of different scenarios about what could happen with sea level rise especially. And some of the business as usual scenarios, it's 3 meters of sea level rise or whatever. But there's other scenarios where it does eventually stop rising and maybe even start coming down a little bit. So it's not totally futile to stop using all these fossil fuels. Yeah.
Well, we had a Saturday seminar.
Yeah.
About in 2005 about this when there was first discussion.
Yeah.
Among the public. I think Al Gore's movie came out around that time.
Yeah.
And we actually had a couple of presentations here.
Okay.
At the Saturday seminar. And actually all the things are actually more than was
Yeah.
predicted at that time.
Yeah. They knew what was going on then. So yeah.
I think we have time for one more question.
Anybody else? Yeah.
Just a quick question.
Yeah.
It seems like most of your data was pretty much a linear rate of change. Now it's becoming exponential.
Yeah.
Is there a chance that you're going to have eventually a chaotic situation where a drastic change also occurs?
Yeah, I mean, there's scenarios like that out there where the Greenland ice sheet just collapses, or some of the ice sheets in Antarctica. We haven't talked about Antarctica. Some of those ice sheets just collapse. Ice sheet modeling is just not in my professional wheelhouse. So I can't speak to any in any great detail about that. But yeah, there are such chaotic scenarios out there. Yeah.
The Gulf Stream reversal is another.
I haven't heard about reversing. I've heard about maybe slowing down. So far, if you look at the data, you don't see that the Gulf Stream is slowing down particularly. It fluctuates. There's a really cool measurement. So, you know where Miami is, right? So right across the Straits of Florida, there's one of the Bahamas, right? One of the islands. And there's a submarine cable that goes between them. And you can actually use that submarine cable to measure the flow of the Gulf Stream, the amount of water that's flowing in the Gulf Stream. You measure the voltage difference between one end and the other. And they've been doing that for several decades now. It goes up and down. It's got a seasonal aspect to it, and it's just kind of chaotic. But they haven't really detected any increase or decrease. Yeah, it's really fascinating. Yeah.
What about the North Atlantic current?
It's an extension of the Gulf Stream, and so I don't.
That's the one that flows the other way with the cold water, right?
So the terminology that I typically use is the Gulf Stream goes off of Cape Hatteras here, wiggles around a whole lot, and by the time it gets to the south of the Grand Banks, it is what you would call the North Atlantic current, and it's still tootling off to the east. Now there is the Labrador current, which comes down from the Labrador Sea, and that would be cold water coming down. Yeah, that might be what you're thinking about. Yeah, there's also a deep western boundary current, which flows very deep, like 2,000, 3,000 meters, right along the continental shelf right there, and that's also cold water coming south. Yeah, it's a fascinating business. I never get bored in this business. So.
No, and if you guys do have additional questions, you feel free to stick around and come up front and ask. We'd love to have you spend a little more time with us this morning.
Yeah.
Thank you again for Dr. Bingham.
Thank you.
And I think we have a couple pancakes left, so feel free to take one on your way out. If you could help us to stack these chairs, that would be much appreciated, and we hope to see you around.